Now we're going to talk interest. We're going to talk about simple interest and compound interest. And this is really a combination of two sections in the text, but they go so well together that I thought we ought to just go ahead and use that as one lecture. So we've got this box that I'm sharing on the screen is straight off of our formula sheet. It's in the top left of the first page. And we're talking about interest, simple and compound. Simple interest is a lump sum. It's the type of amount you say you loan money to somebody and at the end they pay you back plus a single chunk of money. That would be the lump sum that comes with it. And compound interest is kind of where you get interest on your interest, meaning after 1 year, they give you some money back on top of your loan, and the next money they give you money back based on your loan plus however much interest was there before. And this often occurs in savings accounts and investments, things like that. When we get to the calculation, it'll make a little more sense. Then we have this continuous compounding. You really need to watch for that word right there, continuously. If that word is there, then we know we use this other formula. Otherwise, for compound interest, we will use that formula as listed. So we'll need to kind of state what those values represent. I is the interest. So if you're asked to find the simple interest that has been applied, you would use that I formula. P is present value or the principal. It is how much money is available today. It is how much the amount of the loan is, or something like that. It's the first amount. We've got R, which is our interest rate. And that needs to be listed in the formulas as a decimal. Though in the problem, it will often be listed as a percentage. So we need to be able to convert back and forth between a percentage and a decimal. T is the time. And I'm going to say in years, but only because our interest rates are often given per year. If the interest rate is given per month, then the time would be months, but it's almost always years. So I'll go ahead and say that that's in years. N is the number of times your interest is compounded per year. So notice it only shows up in the compound formula. And we've got some words that will help us. If it is annual, then we know that N equals 1. If it's semi-annual, or every 6 months, then we know that N equals 2. If it's quarterly, then we know that N equals 4. Or if they might say every 3 months. If it's monthly, then N equals 12 because there are 12 months in a year. So that would happen 12 times. Daily, then N will equal 365. Now I'm going to write or 360 because there's a banker's year where they looked at 360 days per year. It was easier to do the calculations than with the 5. They only had 2 numbers to multiply instead of all 3, and then you add a 0 on the end. And it also gave the bankers a little bit more money. So it was accepted that they would use 360 days in a year for quite a while. Once we got calculators, they went to the 365, but sometimes you'll see problems that say use 360 days in a year. So that takes care of our various variables that are going to show up in our interest problems. Now, I do need to denote this E here. That is E to the X. It's on your calculator. There's probably a button that says E to the X. As a matter of fact, it may have an ln above it, or you might have an ln button with e to the x above it. Regardless, that's the e we're talking about here. And it actually stands for a very particular number, kind of like pi is 3.14159, etc. E to the x is 2.7182878, and so on. It keeps going forever. But that's the E we'll be talking about there. And you'll find that the key factor to solving all of these problems is knowing how to use your calculator. So I'll keep going back to that a few times and make sure that we're good with using our calculators. Let's take a look at this problem. We deposit $2,000. So that's the amount today. How much is the loan? So that's our p-value. In a savings account, it has a rate of 6%. So that means R is 0.06. Find the interest at the end of the first year. So T would be 1. And they just want the interest. They don't tell us it's compounded, so we know it's simple. And if all they want is the interest, we'll use I equals PRT. Our principal is $2,000. The interest rate is 6%, and time is 1 year. So we just multiply those three together. 2,000 times 0.06 times 1 is $120. So that at the end of the first year, they would add $120 to our account. Not too bad. Make a little bit of money right up front. Let's look at another problem. Let's say we spend $4 each day, 5 days per week on coffee. How much would we spend on this item in 1 year? So let's see, we spend $4 in 1 day. Notice I'm doing a little dimensional analysis here because that helps me solve these problems. 5 days in 1 week for this particular problem, because we're doing it only 5 days out of the week, not all 7. They want 1 year, and we know that there are 52 weeks in 1 year. So let's see what cancels. Weeks will cancel, days will cancel, and I'm left with dollars per year. So remember, we multiply across the top and divide by anything on the bottom. So I have 4 times 5 times 52 gives me $1,040 per year. And now they ask me if I invest that in a savings account with a rate of 5%, how much would I have after 1 year? So I'm looking for how much will I have? That's a future value. So that's the A equation right there. That's the one I need to pay attention to. A equals P times 1 plus RT. So the future value will be the amount I'm investing. That's how much I'm saving by not buying the coffee. My interest rate is 5%, and that's for 1 year. So remember, PEMDAS says I need to, actually not that whole thing, inside the parentheses, I need to multiply first, and then I can add. So 0.05 times 1 is 0.05, and then I can go ahead and add 1 to that. And so I have 1040 times 1.05. And now I can multiply those together, and my future value is 1092. That means, let's see, what's the difference there? That's $52 more. They gave me $52 in interest on my 1,040. So instead of buying coffee every day, 5 days a week, all year, I invest that money and I potentially end up with almost $1,100 at the end of the year. So that can help. One thing I would like to note here is that this next, the formula we used, the A equals P plus RT, was arranged by noting that the future value of our account was our principal plus interest. And we know that interest is PRT. So I could write that out that way. And then I see that there's a p-value in both of those terms. And if I factor that out, I get that more advanced formula. But it should be heavily noted that our future value is the principal amount plus interest. And we will be using that later. When they ask us how much interest we got, we are just going to subtract the principal from the future value, and that difference is our interest. So let's go ahead and find a different kind of problem that uses interest. We borrowed $2,500. That's the amount of the loan, so that's our principal. We promised to pay back $2,655. That's our future value in 6 months. So time equals 6/12, or 0.5 years. Remember, I needed that in years. So what's the simple interest? Well, we've got A, P, and T. The simple interest that uses those variables, the formula is A equals P times 1 plus RT. Let's put in everything we know. A is 2,655. P was 2,500 times 1 plus our interest rate, which we don't know, times 0.5. Okay, now in my face-to-face class, I asked how would we solve this, and they suggested I distribute the 2,500 first. So let's go ahead and do that. I still have 2,655 on the left. Now I've got 2,500 times 1, which is 2,500, plus 2,500 times 0.5, which is 1,250, and I still have the R. Now remember, when we're solving these equations, we start furthest away from the R, and right now the 2,500 is added, so I will subtract that from both sides. And once I do that, I have 155 on the left, and I'm left with just the 1250R on the right. Again, I'm solving for R. It is multiplied by 1250, so I'll divide both sides by 1250. Because 1250 divided by 1250 is 1, so I'm left with 1R. And 155 divided by 1250 is 0.124. And recall that when I'm converting a decimal to a percentage, I just need to move the decimal 2 places to the right, and that leaves me with 12.4%. So that would be the interest rate on this particular loan. One nice thing about this problem is it highlights that I can solve for any one of these variables. I just highlight in the problem what all of the numbers represent, plug those into the formula, and now I simplify and solve for whatever formula, whatever variable I don't already have. Let's look at another problem. We're planning to save $2,000. That's what I want to have at the end, so that would be my A value. Trip to Europe in 2 years. So that looks like that would be our T value. We decide to purchase a certificate of deposit from the bank. It pays a simple interest rate of 4%, so R would equal 0.04. How much must we put in the CD now? So we're looking for P in order to have that 2,000 in 2 years. So let's grab our simple interest formula again. Plug in everything we know. We know we want $2,000. We don't know P yet. We're trying to get that. Our interest rate was 0.04, and we're talking about 2 years down the road. Once again, PEMDAS would suggest within the parentheses, I can multiply first and then I'll add. So multiplying those first gives me 1 plus 0.08. And now I can add. So 2000 would be P times 1.08. I need to now divide both sides by 1.08, reversing the multiplication that is being done on the right. 1.08 divided by 1.08 is 1. So I'm left with 1p. And 2000 divided by 1.08 is 1851.8518 and so on. Now, in monetary terms, we end with cents. Notice that to round this then, using the rules of rounding, I would say 1851.85. However, if I were to plug that 1851 and 85 cents in for P in our initial formula, I would not end up with $2,000 at the end. I would probably have $19.99 and 99 cents because I rounded P down. And so in the problems, they will tell us to always round P up to the nearest cent. So rounding that up means I'm going to disregard the rules of rounding when I'm solving for P. And now I know I will have at least my goal, in this case of $2,000. If you follow the rules of rounding, you may not achieve your goal. So when you're solving for P, and only when you're solving for P, you will always round up to the nearest cent. And the blue text says that. It says round up to the nearest cent, meaning don't follow the rules of rounding when solving for P. That one's just a little bit of a twist. Every other number, we will follow the rules of rounding, but when solving for P, always round up. Let's look at another problem, and we'll jump into compound interest, which is actually 8.4 in the book, section 8.4, but the two combine so well, I thought we could treat them as one. So it says we deposit $7,500. That's the amount of our deposit. That's a p-value. Notice how in these problems, I'm always circling the numbers and writing what they represent. On an exam, I recommend you do exactly this. It's far easier to know where to plug values, and you're more likely to get it right. And so I really recommend you do this. In any event, move on to the next one. This is our rate. So I'll say R equals 0.06. They tell me the interest is compounded monthly. And as we said earlier, monthly means N equals 12. So how much money will we have after 5 years? Well, that's a T. So let's go ahead and plug those in. Now the formula I'm going to use is the compound interest formula. P times 1 plus R over N raised to the NT power. So I'm solving for A. P is 7,500. Got our 1 plus R is 0.06. N is 12. N is still 12, and now T is 5. Now often, I can type this into my calculator and get it all in one shot. Depending on the calculator I'm using, I may need to add an extra set of parentheses around that fraction and perhaps around that exponent to force PEMDAS to follow the rules that I need followed. Sometimes I can, depending on my calculator, type it in so it looks exactly like what I'm seeing on the screen. Sometimes I'll just start here at this fraction and then add the 1, and then raise that to the exponent and then multiply by the 7,500. You'll have to determine which method your calculator will do. practice a few of those and we'll see which one works for you. You definitely need to make sure you get this right. So I'm going to plug this into my calculator. Now with my calculator that I'm using right now, I can type it in exactly the way it looks on the screen. So I can even add the little fraction bars and it looks like a fraction. It's pretty slick. And so I know that this answer is correct because by typing it in just the way it looks, I know that this will follow the rules of PEMDAS, and this will be the answer we get. If you're not getting $10,116.38 when you're calculating this, then we need to take a look at how you're entering it to make sure that you're entering it correctly. But either way, it should work just fine. You know, I actually have an emulator. Let me see if I can bring that up to show the calculator that that I'm talking about here. Maybe that will make it so that you can see just what I'm talking about. So I thought I was bringing it up. Yeah, it just takes a second to load. I'm going to change my share so that I'm not sharing just Photoshop. I'm going to share my entire screen. So you can see this come up. Oh, I've already entered the calculation there. Let me go ahead and do that from scratch again. So with this TI-30XS, and the one I'm using on my desk is the 36X Pro. Looks very similar, but let me show you how I would enter this one. We've got our 7,500, and then I can type an open parenthesis. Oh, I didn't want two of those, just one. And then I can do 1 plus, and I've got this fraction option that allows me to enter the 0.06 up above, and then I hit the down arrow to get into the denominator, and I'm going to hit 12 there, and then the right arrow to get out of the fraction. I'll close that parenthesis, and I will raise it to the 12 times 5 power. And then I can hit enter, and you can see that it looks exactly like it did on the screen, and so PEMDAS worked just fine. Like I say, sometimes I can't quite enter it that way. Maybe I would do 7,500. I may even have to hit the times first, depending on the calculator. I can do 1 plus open parenthesis 0.06 divide by 12, close the parenthesis for that little r over n fraction, and then close the parenthesis for the 1 plus that fraction. And I'm going to raise that to the, and I'll put an open parenthesis, 12 times 5, close the exponent parentheses, and hit enter. I get the same result. Some calculators, I need to enter it that way. And so I really have to pay attention to where the parentheses are that I'm using. But again, practice with your calculator until you get this answer for this problem. If you're unsure, or if your calculator's not doing like you expect, let me know. I may have a version of your calculator, and I can walk you through your calculators. But this is a way for us to use compound interest to solve for a problem. So what's happening is after 1 year, they add 6% interest. After the second year, they don't just look at the 7,500, they look at the 7,500 plus 6% of that, which would be 7,950. And they're going to take 6% of that for the second year. And that's how compound interest works. It just keeps adding the interest and then taking the next year interest on that new amount. Let's look at another problem. Here we have two accounts we're looking at. We need to decide which one's best for us. We can invest $8,000, which would be a P, at 6 years. So T is 6. and we have a choice between two accounts. So we're going to invest $8,000 for 6 years. The question is, do I want a 7% rate? So R would equal 0.07. Compounded monthly means N equals 12. Or do I want 6.85%? So R equals 0.0685. Compounded continuously. There's that magic word that says I use a different formula. So I'm going to compare both. Let's do a better table here. P is 8,000, T is 6. And we have two options, either R equals 0.07 and N equals 12, or we have R equals 0.0685. We're going to use the E now. So let's take a look at those. We've got A equals P times 1 plus R over N raised to the NT power, or we have A equals P times E raised to the RT power. Let's plug in what we know. We've got 8,000 times 1 plus 0.07 over 12 raised to the 12 times 6 power. Or we have 8,000, oops, I was doing 88 for some reason. 8,000 times E raised to the 0.0685 times 6. All right, so plugging these into my calculator, I'll do the 8,000 times 1 plus R over N, 0.07 divided by 12. And I'm going to raise that to the power. And that gives me 12,160 and 84 cents. Or this other option, I'm going to take 8,000 and I'm going to multiply that by E to the 0.0685 times 6. And that gives me 12,066.60. So while the continuous compounding it's kind of like an N value of 1,000 or more. While that would compound more often, because the interest rate is lower, it turns out that compounding monthly actually pays more because this one has a higher interest rate. So that would be the preferable account. We would get more money. It's not a big difference. Looks like it's about, what do we have? 134, no, $106. No, $94. Oh my goodness, I can add. I'm trying to subtract though. Okay, so that gives us a sense for how we can compare two different problems. Let's look at, we've only got a couple more problems to do here. So how much money should be deposited today? So we're looking for P in an account that earns 6% interest. So 0.06 would be R. Compounded monthly, so N equals 12, so that it will accumulate to $20,000. That would be A. In 5 years, that would be T. So because they gave us a compounded rate, the monthly, we know we're using the compound interest problem without the E. Once again, we're solving for P. So A would be 20,000. We don't know the p-value yet. Our interest rate is 0.06. N is 12. Raise it to the 12 times 5 power. So I'm going to treat this whole thing after the P as if it's 1 unit. I'll just go ahead and plug that part into my calculator. So we have 1 plus 0.06 divided by 12. And I'm going to raise that to the 12 times 5 power. It might be just as good to do 12 times 5 and recognize that's 60, and then raise it to the 60th power. Then you might avoid some errors potentially. But I have this equaling 1.34885. I'm just going to keep that in my calculator. There are more numbers after that, but I want to divide both sides by that value. And I'm not going to type everything into my calculator. I'm going to show you a little trick here that I find very helpful, because most scientific calculators seem to store your latest answer in a variable called ANS. You may see something down by your equals key that has ANS, and I'm going to use that. So what I end up with is I'm going to divide, oh, I forgot a 0 there. Be careful with that. I'm going to divide 20,000 by that ANS. I don't clear it. I just hit 20,000 divide by ANS. And on this calculator, it says answer, but that gives me the p-value. That way I don't have to write down a great big number and then clear it and type everything in from scratch. I can just take advantage of the fact that it had a whole bunch of numbers in it, and I can use that variable. Oh, I'm solving for p, so I need to round up, even though the rules of rounding would suggest I needed to round that or keep that 5 at a 4. I need to round up because I'm solving for p. So there we go. Actually, I could probably bring up this other calculator and show you what I meant. So I'm going to clear this. We had, let's see, let me pull this back so I can see. I'm going to go ahead and do 1 plus that ratio of 0.06. And I'm going to divide that by 12. I'm going to get out of that fraction, close the parenthesis, and raise it to the, like I said, 12 times 5 is 60. And that gives me that 1.34885. Now notice down here, right above the minus sign, it says ANS. That's what I was talking about. So now I'm going to enter 20,000. And I'm going to divide that by that ANS. Now that's in the green, so I need to hit second. And then I can hit that, and you can see it's 20,000 divided by the previous answer. And there's the 14,827 and 44 cents. But again, we're solving for p, so I had to round it up to 45, even though the rules of rounding would suggest I needed to round down. So that's the ANS I was talking about. Mine was above the minus key on that calculator. It's above the minus key on the calculator on my desk, but I've got another calculator that actually has a button that says ANS on it. So we'll use the whatever calculator we have and make it work for us. There's one final idea here that I do want to talk about, and that's effective annual yield. And I left the definition up there. The formula is on our formula sheet. It's over to the right side, though. I'm not sure why we added it over there, but that's where it's located. And it says, suppose that an investment has an interest rate and pays compound interest so many times per year. Effective annual yield is the percentage rate that I would need on a simple interest account to give me the same amount of interest that I'm making on my compound interest account. And it allows me to compare the two a little more directly without having to run through all of the calculations. I can just do this one calculation and it lets me know the difference. So let's see what we're talking about. We have a savings account here in the problem with a rate of 5%. So 0.05 is the rate. Interest is compounded daily, and they tell me assume 360 days per year. So N would equal 360. They want me to find the effective annual yield. So I'll take that formula we have up above, and I am just going to plug in all of the values. Notice I write out the full problem, the equation first. It seems to help me make sure I'm entering things in the right place. If that works for you, use it. Whatever it takes to help us do a more accurate job, I say we should do it. As long as it's within the rules, right? Okay, so now I've got this formula and I can type that into my calculator. I'll go ahead and bring up this other calculator. I'll clear it so we don't have any distractions there. We've got 1 plus, and I'll go ahead and bring up that fraction, 0.05. Drop this down, divide by 12. And I need to close that parenthesis, raise that to the 360th power. I'm going to hit the right arrow to get out of the exponent there because I need to subtract 1 from the overall. And I hit enter and I get 3.4677. Now that seems a little high to me. Did I mistake what I was entering in? I don't think, oh, I entered 12 as my denominator. It should have been 360 for the denominator. That's what did it, because that number didn't look right to me. Let me do this again. You can see I get so used to using certain numbers, probably just like you do, and sometimes I make a mistake. So I'm glad I saw that and I got to check on that. That just seemed a little too high. I expect a decimal less than 1. There we go, that's a little better. 0.0513. 0.0513. And now that's a decimal, so to make a percentage out of it, move the decimal over twice, and that equals 5.13%. So if I had a simple interest account that gave me 5.13%, I would get the same amount of interest as I do with this compound interest account that gets 5%. And so now we can compare those with just percentages. So if you're out, say, searching for a new car or something, and you go to various banks to see which will give you the best rate, you can, well, they'll give me 3%, but it's compounded quarterly. They give me 3.14 compounded monthly. They give me, oh, let's say 2.68, but it's compounded daily. In order to compare all three, I can plug all three individually into this formula and then just compare what the comparable simple rates would be. And now I know which one is the best deal for me. And so those are the types of formulas and calculations we will use to calculate interest, both simple and compounded interest. And watch for keywords like monthly, daily, semi-annually, quarterly, to recognize that there's an N needed. If it's got that magic word continuously, we use that other formula. So watch for that one. You'll only use that formula if it is continuous compounding. Otherwise, you'll use the other. And now, if they wanted us to calculate the interest, I think I didn't share that particular type of problem. So let me add that to this one. So after 5 years, oh, it was in the problem, but I skipped it. Okay, sorry. So after 5 years, so our problem was A equals P plus I. And we're solving for interest. So now we know our A value. And the P was given in the problem as 7,500. The question is, how much is interest? Those two are added together. In order to reverse that, I would subtract. And those two will cancel, leaving me just interest. So 10, 116, and 38. I'm struggling typing in my calculator for some reason. Minus 7,500 gives me 26.16 and 38 cents. So that's how much is interest. Notice it said find the interest, and I didn't go to any of the interest formulas. I just recognized that the amount I have in the account today minus the amount on day one is interest. And so if you're to find how much interest you paid on your car over 5 years, just add up all of your payments and subtract from that the amount of the loan, and the rest is interest. You won't use these formulas to calculate the interest. What you will do is you will use your future value and subtract the present value, and that will give you the total interest. So I hope that helped. Again, like always, if you've got questions, let me know.